All right, let's take a look at an annuity problem. So what we have here is a deposit of $200 being made at the beginning of each month into an account that pays 6% interest compounded monthly. And what we want to do is we want to find um, the amount that's in the balance of the account after 2 years, okay? So we're going to use the compound interest formula that says the future value is equal to the present value multiplied by 1 plus the interest rate, the yearly interest rate I, over n, which is the number of times interest is paid per year. So this is the yearly interest rate divided by the number of times interest is paid per year, raised to the power of n, which is once again the number of times interest is paid per year, times t. All right? So in our case, what we have here, let's take a look at the very first payment. The very first payment is made at the beginning of the first month. It's a payment of $200. That $200 has a future value of, let's see, this 1 plus R, which is 0.06, over N, which is 12. This this arithmetic gives me 1.005. So this factor here, 1 plus I over n, actually amounts to 1.005. This first payment of $200 has that factor 1.005, and we're compounding n times t, which is 12 for n and 2 for t, because it's monthly. Monthly means n is equal to 12, right? And for 2 years, so t is equal to 2. So this first payment is going to be compounded 24 times. Basically, you get 24 interest payments for this first $200. All right. The second $200, the one that you deposit at the beginning of the second month, well, that one is only going to be compounded for 23 months. So it's 1.005 is only going to be raised to the 23rd power. And it continues like this. The next payment of $200 is only going to be compounded for 22 months. 0.005 for 22 months. And it continues on in this fashion, continues on all the way down to, let's see, we have in the second to last month, that $200 that you deposit is only going to be compounded for 2 months because you're in the second to last month. So we square this. And in the last month, that $200 that you put in the last month is only going to get 1 month of compounding. So you'll only get paid interest on that last $200 once. All right, so there you have a sequence of payments. These are all the future values for my sequence of payments. These are all their future values for all 24 payments that I've made. What I want is I actually want the sum of these 24 payments. In terms of a sequence, this would be the 24th partial sum of this geometric sequence. All right? This is the geometric progression. We have the, let's take a look at this last payment that was made, $200. 200 times 1.005 plus the next payment of $200. This is going to be the total amount in the account. All the future values of all these payments added up. 0.005 to the second power. And then you keep going like this all the way up to 200. The very first payment we made, which was compounded 1.005, was compounded 24 times. So this is the balance in the account. This is what the balance in the account is going to look like. This is actually the 24th partial sum of this, which is going to turn out to be a geometric sequence. This is the 24th partial sum. 24th partial sum. So let's see. Let me do a little bit of simplifying here. For instance, you notice that 200 times 1.005 is a factor of every single term. So I can factor that out. 200 times 1.005 is a factor of all the terms. When I factor it out, well, when I divide it out of the first term, I'm left with a 1. When I divide it out of the second term, I'm left with 1.005 to the first power. When I divide it out of this third term, I'm going to be left with 1.005 to the second power. And I continue on in that fashion. And when I divide it out of this last term, I'm going to be left with 1.005 to the 23rd power. Okay, so I still have this 200 times 1.005. And now the inside of this bracket is a very simple geometric sequence. Let me write it this way. As a sum, it's going to be the sum from I equals 1 to 24 of, well, the first term is 1, and then the common ratio is 1.005, and I'm going to raise this to the power of I minus 1. So if you take a look, when I is equal to 1, this is 1 minus 1 is 0, and 1.005 to the 0 power is the number 1. When I is equal to 2, you get 2 minus 1, and you get 1.005 to the first power. This one. When I is equal to 3, you get 3 minus 1, and you get 1.005 squared, which would be the next term. And when I is equal to 24, you get 1.005 to the 24 minus 1, or 23rd power. So this is the summation, the sigma notation form of that sum there that I use the ellipse to represent. All right, this is the 24th partial sum of a geometric sequence, which I'm going to use to find the 24th partial sum of my sequence. So it's going to be 200 times 1.005. And in order to find the 24th partial sum, this is the nth partial sum formula with n equal 24. It's going to be A1, which was 1, remember, times 1 minus 1.005 raised to the power of 24, this number right here, 24, divided by 1 minus 1.005. So this calculation will give me the sum of all those annuity payments. It'll give me the future value of all those payments, or the balance that is in my account after 2 years. All right, so let's do this calculation here. So we have 1.005 to the 24th power. Let's do that. We have 1.005 raised to the power of 24 equals, that's this number right here, 1.12 blah blah blah. That's 1.005 raised to the 24th power. What I'm going to do is I'm going to take that answer and subtract it from 1. So it's going to be that answer minus 1 gives me this number, 0.12, or negative 0.127 blah blah blah. Okay, so that's the numerator of this fraction. That's the numerator of this fraction. And then I'm going to divide by 1 minus 1.005. So I'm going to divide that by, and I'm going to open a parenthesis, 1 minus 1.005. Close my parenthesis, and this is equal to, so this factor over here in the bracket, this factor over here, amounts to a 25.4 with all those decimals. All right, I'm going to take that and multiply it by 1.005 and multiply that answer by 200. So times 1.005 and then multiplied one more time by 200. So I get the 24th partial sum to be $5,111.82. $5,111. So we find out that the balance is $5,111 and what did I say, 82 cents. So all those payments, all 24 of those payments amounts to $511.82. That's the sum of all those payments that made up that annuity. Now, one last thing I want to note here is if you just made 24 payments, if you just made 24 payments of $200 without um, any interest being accrued, it would amount to $4,800. So the difference between $4,800 and $5,111.82, that difference is the amount of interest that we have earned by putting it into an account that bears 6% interest monthly. So that is an annuity problem.